welcome to those who are joining now. People still joining. Just give them another little minute and then we will start. Greetings, Cheyenne. And we have some questions starting already, which is very exciting. Please do put your questions in the chat and we will collect them all together at the end for James, and he'll do his best to answer them. We traditionally have excellent questions from this very knowledgeable audience to challenge our speakers. Excuse me. Good. Okay, I think we'll make a start. Oh, there's just a couple more people arriving now. As greetings, Matteo, who is a Sun member. Fantastic to have you with us, Matteo. Good. So just to introduce everybody, you should be able to see myself, James Cornish, and some slides on Sun. So if that's not showing on your screen, you might want to try and readjust your screens to be able to see that. So just to briefly introduce the Space Universities Network to you. This is an organisation set up by the space higher education community for the space higher education community. So I'm afraid it's not open to students, but it, excuse me, it is open to your staff. And our aim is to support those staff in sharing ideas of good practice and sharing resources and organising things for all of our members to share with their students. So we hope by that we get fantastic speakers like James in these webinars to come and speak to all the students all around the UK, not just to one university. So it's a really nice way of sharing exciting new topics like we're going to have today. So it's myself, Kate Smith, and from Manchester, Ian Raper from UCL, and our coordinator, Charlie Leach, who you'll meet in a minute. We're sponsored by the UK Space Agency, and the University of Bristol kindly hosts the websites. So what is Sun? I've just explained we provide resources and events. These are all our members. If your university is not on the list here, please could you either drop me a line, I'll put my email in the chat in a minute, or talk to anyone who teaches you space and say, have you heard of Sun? It's free to join, and they seem to do a bunch of stuff for space. That would be amazing if you could do that. You can see slightly the kind of things that we try and encourage, that is courses, resources, and the resources could be anything from video clips to case studies that we've put together. We have meetings, regular meetings, including a summer workshop, which this year we did on sustainability. We provide links to outreach and careers. And that's about it from me. So I'm going to pass on to Charlie, our coordinator. Thanks so much. And I'll try and stop sharing.
Cool. Hi guys, I'm Charlie and I work as coordinator for Sun. So if you have any technical difficulties during the webinar, send me a direct message and I'll try and sort it out for you. We're very lucky to have James Cornish here today to speak to us. James is an advocate of utilising novel technologies to achieve net zero. He has 10 years experience as a systems engineer across the energy and defence sectors. Recently stepping across to the space sector, James is now leading the Frazer-Nash Space Business and represents them as the founding member of the Space Energy Initiative. This brings together government, research and industry to develop and deliver a coordinated program of space-based solar power. A veteran of large-scale nuclear new build and infrastructure projects, James has an in-depth understanding of how to and how not to successfully deliver such projects. This talk will explore the status of the leading space-based solar power programs and examine the various challenges standing between the concept and making them a reality. The structure of the talk will be about 30 minutes from James, and then we'll open the floor up to you guys for a Q&A. So do remember to put your questions in the chat as we go along. Just so you know, this session is being recorded, and that does include the chat as well. So without much further ado, I'll hand over to James.
That's great. Thank you, Charlie. Firstly, can I just check, can everyone see my screen?
Yeah, I can see it.
Excellent. It's great to be here tonight to speak with Sun. I'm really excited to talk about SBSP and the advances in the technology and the momentum that's really building around SBSP. So, given the audience, I was thinking, how can I pitch this? And chances are you might be applying for a job with an SBSP development company in the not too distant future. So my role tonight is to brief you for that interview. So what do you need to know? Well, firstly, what is space-based solar power, or for short, SBSP? And why is now the right time for SBSP? Why wasn't this done 20 years ago? Or why isn't it some far-flung future technology? What are the key technical challenges to achieving a viable SBSP product? And what's the economic case? Do the numbers add up? And then how do you deliver it? So what are the drivers for SBSP? And there's two main ones. The Paris Agreement, signed back in 2015 by over 150 companies, set out to limit global warming to well below 2 degrees Celsius, preferably nearer 1.5 degrees. And you were seeing in the news, how do we achieve this? It's a matter of moving to what we call net zero carbon emissions. To achieve that, we're going to need see a massive increase in the amount of generation capacity in terms of electricity that we'll need. And presently, we are not on course to achieve this, the UK and globally. In terms of that growth in electricity demand, we're looking at least a doubling of the amount of electricity required to achieve, if we're to achieve net zero. So what's driving those three key things? Well, the first thing is population growth. In the UK and globally, we have a growing population. So even if people continue to use the same amount of electricity, we've still got more people, we're going to need more generation. The second driver is economic development. So there is a direct correlation between economic development, between civilizations developing, and the amount of energy they use per person. Greater wealth requires greater energy. And I know there are philosophical arguments on that, but that is the reality we find ourselves in. The other element of increased generation is moving away from energy use at source. So, for example, cars, how we heat our homes, how we cook our food. Rather than burning oil or gas or petrol at point of use, we generate that power at large power stations or modular, smaller power stations or micro generation, and then we pipe it to wherever is necessary down the grid, and you use it in the form of electricity. There are three key success criteria to achieving net zero in terms of electricity supply. So the first is obvious. We need this to be zero carbon. We need zero carbon or low carbon sources of generation. But it also needs to be secure, and it also needs to be affordable. And the recent war in Ukraine has really demonstrated why these are critical. we are potentially facing in the UK and Europe, where there is the possibility, if slim, of blackouts. And that has a profound impact on not just from an economic perspective, but individuals. So we must have a secure and affordable supply. Now, there's two words I'm going to be using when we go through this presentation, and I think it's worth setting these out now. The first is baseload. And baseload is the amount of energy that you always need on any grid. It's the minimum amount of use. And then throughout the day, throughout a particular cycle, you will see fluctuations, whether in the morning or evening, and also fluctuations over seasons in terms of how much electricity you need. But that bottom bit that's always coloured in on the graph, that's what we call baseload. So you always have to be generating that amount of electricity. The second word is called intermittency. And that's talking about intermittent energy sources, and that is renewable energy. So renewable energy, wind, terrestrial solar, is intermittent. So you won't always be able to achieve that baseload with intermittent renewable sources unless you have some kind of storage. And there are lots of technologies which are being developed at the moment, from advances in battery technology to pump storage and various other innovative technologies that might possibly, with lots of development, achieve the required storage that's necessary. So I describe net zero as an evolution. These generation technologies have existed for a long time, 20, 30 years in their current formats. And yes, they've improved, but it's been an evolution. The second driver is a transport revolution. Access to space is going through a revolution. In 2013, we launched just over 100 satellites into orbit, and we thought that was a really busy year. In 2020, we did 10 times that figure, well over 10 times that figure, with just over 1,200 satellites. And what's driving this? It is primarily down to the reduction in launch costs. Launch costs have fallen since the days of the space shuttle by 2 orders of magnitude. And as many of you will know, working in the sector, it's been, or studying in the sector, it's been driven by reusable launch vehicles. And where SpaceX is leading with Falcon 9, others are following on their heels, trying to get a piece of the market. Launch costs are forecast to fall at least 1, possibly 2 orders of magnitude further with the introduction of fully reusable launch vehicles, such as Starship and Reaction Engines Limited's Skylon spaceplane. So launch costs are having profound impact on the economics of space, and it's allowing us to put up significantly more kit into space, significantly more tonnage. And we're going to move away from having space systems which are deliberately kept as far apart as possible to actually building bigger and bigger structures, and that's all enabled by the fall in launch costs. Autonomy is another key area. Now, I'm really hopeful that we don't have a repeat of HAL 9000s whizzing around in orbit, but autonomy is going to be absolutely key. Being able to have space operations which function by themselves. So that could be autonomous robotics, autonomous assembly, autonomous maintenance, IOSM, those kinds of things. So, and that technology is being used now in terrestrial applications, and we are well on the path to achieving a complete autonomy of various systems. The final area in terms of SBSP and space, and there's an enabler, is finance. So reduction in launch costs, reduction in risk are now making significant space projects such as SBSP more palatable to financial institutions such as investment banks, angel investors, and others. And they are looking for a reliable return. So they're not going to sign up to create crazy schemes. They want to have a reliable return on their finance. And that's something we can start delivering as the space economy evolves over the next 10 to 20 years. So your next interview question, space-based solar power, what is it? At its heart, it's really very simple. what we do is we have a very large, over 1 kilometer long space satellite in orbit. And this satellite is about 2,000 tons, so it's only about 4 times the weight of the International Space Station, but being much, much larger. It's a very diffuse structure, and it's out in geostationary orbit. It's out in geostationary orbit, and it's you collect sunlight using large reflectors and concentrate that sunlight down onto photovoltaics, so solar panels. And there are various technologies you can use, whether it's thin film or concentrated. Concentrated seems to be the leading technology, and that you turn those photons using that PV into electrons. You then convert those electrons back into photons in the form of microwaves, and you can beam that power from geostationary orbit back to your ground station on Earth. Now, if you're doing this from geostationary orbit, and depending on the particular concept you're looking at, one of the reasons why the satellite has to be so big is to be able to make sure that that beam doesn't have too high intensity. And your ground receiver on Earth is quite a diffuse structure. You can potentially have dual use of the land below it. But it's a large structure. It's typically measured in the 10 and low 10 kilometer range in terms of rate and in terms of diameter. Now, we mentioned the word baseload earlier. One of the advantages of space-based solar power is it can provide baseload power. Because it's in geostationary orbit, it's always seeing the sun. In fact, you do have slight intermittency due to going to the Earth's shadow, but this is typically only 45 times a year in geostationary orbit and ranges from a couple of minutes up to 70 minutes at the equinox. Now, the concept you can see on the screen is an example of one space-based solar power concept, which is called Cassiopeia. This is designed by Ian Cash from International Electric Company based in the UK. And this is the leading space-based solar power concept from the UK. There are 2 other kind of SBSP project concepts that are certainly worth mentioning. There's SBS Alpha, which is from John Mankins in the US, and the Chinese are also heavily investing in a SBSP concept. So, is SBSP technically feasible? As Charlie said, my background is actually nuclear engineering, and I know the former head of design authority at Sizewell B Power Station pretty well. And they had an interview question they used to ask new people who come for interview for a job as part of the department or as part on the station. And the question was this: is nuclear safe? And if people answered yes, they didn't get the job. If people answered no, they didn't get the job. But if they answered yes, but, they got the job. And it's the same thing here. Is SBSP technically feasible? Yes, but. There are risks and there are areas which require investment in technology. But all the fundamental physics, all the fundamental technologies are there. This is a development process, we don't need any massive breakthroughs in terms of the technology. We don't need anything to be invented from scratch. So some of those key areas which require some work. So reflectors. Capturing that sunlight from space, you want to be concentrating it down onto your solar PV. Now, those are very lightweight, very thin structures, and they are huge. They're massive structures, hundreds of meters long. So how do you package those up? How do you get them into space? How do you unfold them? Think James Webb solar shield, but on steroids. So a really interesting technical challenge. And how do you keep them to keep forming their shape? So really interesting technical challenge. The second area is power beaming. So you're looking at beaming gigawatt power from geostationary orbit to the ground. The Cassiopeia reference design looks at between about 1.4 to 1.6 gigawatt worth of power. So within the power beaming community, we've actually demonstrated high power beaming at short scale, and we've also demonstrated low power beaming at longer scales, but we've got nowhere near combining both and the distances that are involved. So there's significant work to be done in being able to demonstrate power beaming as a technology. And I did spy that Tom Thorpe, one of my colleagues, has joined the call, who's our expert in power beaming. So I would ask Tom no difficult questions on power beaming, because I will ask you to answer them. SBSP is a very diffuse structure. So I mentioned it was about four times heavier than the International Space Station, but was significantly larger. So how do you maintain the structural integrity of that structure? How do you maneuver it? It's a real challenge, needs development and thought. The thermal management is also a key issue. So when you're beaming power, you've got a really good energy heat sink there. You can beam the heat away and down to the ground. It's a really good way. But what happens when you turn the power beaming off? How do you manage the thermal heat that you're generating? So each individual space-based solar power station will not, being several thousand, a couple of thousand tons, will not be put into space in one go. It will require hundreds of launches of Starship type launch vehicles. So you will have to assemble this. So begs the question, where do you assemble it? Do you do it in low Earth orbit? Do you do it in MEO? Do you do it in GEO? How do you move it between different orbits? And actually, practically, how are you going to assemble it? How are you going to use autonomy to do that? What do those robots look like? What do the modules look like? How do they interact? Decommissioning is a big open question. You can't crash a 2,000-ton satellite into the South Pacific. It's not environmentally responsible. It's not economically sensible. So how do you decommission these satellites? Can you reuse the material for other purposes, or can you keep extending the life of these the satellites? So one of the core design features of space-based solar power is they are what we call hypermodular. So they actually consist of only about 8 to 10 different systems, depending on the content. But each system is made up of lots of the same modules. What we're talking about is iPhone economics in space, loads of the same individual modules. So could you swap them in and out and actually keep the asset generating electricity indefinitely and have a steady stream of material to and from your space-based SBSP? Finally, launch services. So actually launch services in terms of Starship and other competitors are actually relatively well along the TRL map. But the question then is we might have a number of Starships operating, but to launch multiple SBSPs, we're going to need hundreds, if not thousands of launches. So will those be there? Will we be able to scale sufficiently? So is it technically feasible? Yes. But there are some areas which certainly need investment and development. So next question, is SBSP economically viable? So Frazer-Nash, in collaboration with London Economics, has just completed a piece of work for the European Space Agency, where we've undertaken a cost-benefit analysis for SVSP for Europe. And what does it look from a European perspective? And we've concluded that given a 30-year operational life of a fleet of SBS satellites starting in 2040, we could actually see 183 billion euros of net benefits to Europe. Now, how is that made up? So firstly, the first category is avoided terrestrial generation costs. So what does that mean? Well, that's displacing other generation on Earth. So that could include coal, gas, others, by doing it more cheaply in space. And that does also include the cost of carbon credits for fossil fuel technology. You've then got the avoided CO2 emissions. So space-based solar power is a low carbon emitter power. So we're avoiding the cost of actually emitting all that CO2 and the follow-on impacts of emitting that CO2. The third area is R&D spillovers. Now, a lot of the technologies that are required for space-based solar power, such as power beaming, autonomous vehicles, concentrated PVs, have both other space and terrestrial applications. So we can apply these technologies elsewhere and get benefit from them. And the final one is the opportunity cost of land. So rather than using land, productive land for solar, terrestrial solar or wind, and that land can't be used for other things, then we can actually use that for agriculture, for example. Now, those benefits are balanced against the cost, and those are divided into three categories. So you've got the capital expenditure, CapEx, you've got the R&D program to develop SVSP, and then you've got the operational costs of a fleet of SBSP satellites. So that gives us our total benefits of 183 billion euros. So one of the other elements that we've done is looked at what's called the levelized cost of electricity and the value adjusted levelized cost of electricity for SBSP and compared that against other forms of generation. Now, levelized cost of electricity gives us a way of comparing different electricity generation sources, such as fossil fuels, renewables, and nuclear, with space-based solar power. It is slightly coarse, though. It looks at individual technologies and doesn't necessarily take into account all of the grid considerations when you're looking at a whole system as opposed to the individual technologies. So you do have to take this with a pinch of salt. But SBSP, our work has shown that SBSP can deliver a megawatt per hour price that is comparable to nuclear and renewables, and also cheaper than fossil fuels. So, as part of the work we've done for the European Space Agency, we looked at a whole number of sensitivities and how they affect that overall economic case. And two of the biggest ones I've pulled out here. So the first one is the hurdle rate, and the hurdle rate is best described in layman's terms as the cost of financing. So if you've got private investors, commercial investors who are looking to invest, they will want a return on the money they're going to lend you to develop your wind farm. So the hurdle rate for renewables technologies, established renewable technologies, wind, onshore and offshore wind, and solar, terrestrial solar, is about 5%. For nuclear, it's a bit more risky, takes more capex, delays can lead to significant cost overruns. You tend to see a hurdle rate of about 10%. For new power generation technologies, 20 to 30% is a reasonable figure, and we've gone with 20% in the study. And you can see the impact from left to right of those different hurdle rates on the levelized cost of electricity. Now, in our study, we actually looked at, because the concepts for space-based solar power are relatively immature, it's the way to manage that in terms of the work we've done is we took a probabilized approach looking at it from a cost-benefit point of view. So here you can see in the graph the 10% confidence case, the 50% and the 90% in terms of the megawatt per hour. The other area which we were sensitive to was the cost of space lift. So how much it costs to put things into orbit. The 450 euros per kilogram case, that's where we have fleets of operational starships working, and then right up to actually existing space lift technologies. But if you look at the various different scenarios for space-based solar power, there are not many, well, there's in fact actually only one in the work we've done where SBSP doesn't deliver a net benefit to Europe. And that is when, that's when it costs double the amount to develop space-based solar power. But we are on that very fast net zero trajectory where we're developing and deploying lots of renewable technologies, and we're going to hit 2050 our net zero ambitions by 2050 or sooner with just those technologies. And it's worth stressing we are currently not on that trajectory. So our base scenario gave 182 billion pounds worth, billion euros of benefits. If you carry on as business as usual, as we are now, you actually see an increase in the net benefits to Europe, because it gives an opportunity for SBSP to contribute to the decarbonisation, contribute more to the decarbonisation and achieving our net zero targets. So, how do you deliver a space-based solar power program? Most SBSP programs out there, in terms of the literature they put out, concentrate on four key phases. The first phase is ground-based trials, and this first phase, 5 years, for example, is really about de-risking those and retiring the risks for some of those critical technologies. So power beaming, being able to demonstrate meaningful power being beamed over a long distance, whether that be from a ground or maybe from a balloon in high up in the atmosphere. And that's really about building investor confidence. The second phase is then actually taking the technology into orbit, and this type of mission would be launched on a single launch vehicle, but would demonstrate that power can be beamed from orbit. The third phase is then actually scaling that, moving beyond low Earth orbit, and actually beaming meaningful megawatt power from MEO, for example. And actually, one of the options here is to commercialize that power. You'll be delivering megawatt power. You can be selling that back to the grid. You can have energy companies you can sell that power to. So you've already got built in a commercialization route before you get to your final technology state. And then the final phase is, which would be another 4 years, is actually developing a pre-production prototype of a gigawatt generating station out in geostationary orbit. So this has been adopted because space is a really challenging environment in which to do product development. So de-risking those key technologies and ground-based trials is going to be really key. And actually, at each stage, being able to demonstrate that those technologies are advancing and actually demonstrating success to bring investors aboard. So this can't be a fully publicly funded enterprise. It will require private investment. As we go through, diffraction physics in the beam means actually the scale of the system will increase as we go further away from Earth and we end up in geostationary orbit, and that's where we get our very large space-based solar power satellites. And it's worth noting that low Earth orbit. So why don't you put SBSP in low Earth orbit? Wouldn't it be easier? Well, unfortunately, by the time because you're in low Earth orbit, you're zipping across the sky so quickly. So by the time you've acquired the beam and being able to meaningful power, you've already disappeared over the horizon. So there are some applications, but they are limited. So some of the key risks. Now, I'm not going to go through all of these, but I've highlighted some of the key ones. So from a political perspective, now I'm actually the chair of our local parish council here in Swindon Parish. And if you wanted to build a rectenna site sort of on the outskirts of the village, I politely tell you where to go. And getting local community buy-in, understanding how you're going to use the land, where you're going to put these things is going to be a key issue. Now, you can co-locate them, maybe with wind farms. You can put them out at sea in the UK. If you've got a vast expanse of unused land, maybe in the US or Africa or other places, then actually maybe people won't mind. But that's going to be one of the key topics. From an economic perspective in terms of risks, if we really go for net zero, if we see a step change in how we're rolling out other renewable technologies and their levelized cost of electricity really falls off the cliff, then the economic case for space-based solar power starts to actually unravel, as you've seen in the sensitivity analysis. But we're not on that journey, and that will require a substantive change in the route on the journey we're on for that to happen. From a social point of view, and coming from a nuclear background, this is familiar territory. You've got to demonstrate that this is safe. So being able to demonstrate that actually, if you have wildlife flying through the beam, if you have humans flying through the beam in aircraft, it's perfectly safe. And the reference design for Cassiopeia has about a quarter of the intensity of sunlight. So it's thought that's safe, but that needs to be demonstrated, and then that needs to be communicated. Now, we've already talked about the technology, and actually the wireless power beaming is one of those really key technologies that we have to demonstrate actually works. And that will be a key to being able to build confidence in space-based solar power. From an environmental safety standpoint, I think I noticed a question about the launch, the carbon emissions from launch. Again, that's a really good question. I'm looking forward to talking about that more. So yes, that will be important. That's one of the risks. How can you climb to be a carbon zero technology if you're generating carbon? Absolutely. And how can you minimize that? But decommissioning strategy, orbital debris, how do you manage that? How do you do it sustainably? And finally, from a legal perspective, you're going to be beaming gigawatts of power down in the microwave spectrum. The allocation of frequencies, how do you make sure that, because even a slight bleed of that into frequencies which have been other people are trying to use, will completely scupper any form of communication. So how do you regulate that? How do you assign those frequencies? So to summarize, net zero and revolution in space access are the enablers for SBSP. That's what's really enabling it. That's why this is happening now and not 20 years ago, or maybe as a future technology. So if you're ever asked what SBSP is the concept of capturing sunlight, converting it and beaming it microwave power from space. It is technically feasible, but there are areas that require development like power beaming. It's economically feasible, but it is sensitive to the cost of finance and launch costs. And a potential development program could cost 16 billion euros and take up to 18 years. So before I finish, I'm just going to a little plug for FrazerNash, company I work for. I know we've got a lot of people looking potentially for future careers on the phone. So just highlighting, FrazerNash's graduate application are open at the moment. We're looking to recruit about 100 graduates for start in September 23, and we're also recruiting for year in industry and placement students to join us during the summer. If you are looking to get involved in space, there are 4 key areas, 4 key job applications you want to keep your eye out for. Those are the embedded control graduate engineer, and that's kind of working with small satellite developers and looking at their control systems. The artificial intelligence and machine learning, we're looking at autonomy in space is a big area for us. System technology graduates, really focusing on space-based solar power, and fluids and thermals, again, similar with some looking at chemical propulsion. In terms of the package, it's an attractive package. We offer 31,000 starting salary. You get a joining bonus of £2,000, and you also get an additional bonus, which we all get, which is linked to company performance. Placements all year in industry get a salary of 21,000 prorated for the time you're out. So if you're here for the summer for 3 months, you get 3/12 of that. You get 25 days holiday, plus a sale and purchase scheme, and we have a flexible working policy, and you get the usual pension, medical insurance, professional memberships paid as well. So the key notes, key dates for you, and towards the end of October is our application deadline for placements, and then it's mid-December for graduates. All details can be found on our website. Just Google Frazer-Nash Early Careers. Email address on the slides if you want to talk, if you would like some advice in terms of applying to Frazer-Nash, if you're interested in space and want to find out more what we're doing, please do not hesitate to get in touch. But thank you for listening. Love to take your questions.
Cool. Thank you very much for that, James. That was great.
Thank you so much, James. That was really fascinating. So Charlie, do you want to do the questions in the chat first, or your questions?
Yeah, I think we go straight to the questions in the chat. I know we had an initial one about the carbon footprint, and I was just wondering if you could elaborate on that a little bit.
Yeah, no, thank you, Charlie. So yes, obviously, if we're launching, requiring hundreds of launches or thousands of launches for a fleet of space-based solar power, that comes with a carbon footprint. The other things as well in terms of the carbon footprint is actually we're looking at photovoltaics. They require precious metals. That requires a significant amount of mining. So it's not to say that SBSP doesn't have a carbon footprint. It does. It's significantly less than fossil fuels, and it's comparable to others. There are ways you can reduce that carbon footprint, so you can increase the efficiency of your overall system, which means you need to put less mass into space. And then that reduces your total number of launches. If you look further into the future, SBSP provides a really good market for space mining and delivery of material into Earth orbit for manufacture and producing space-based solar power stations. And if you're doing that, then you can remove the amount of mass that you have to launch into space significantly, therefore reducing the environmental costs. Now, that's not considered the plan for most SBSP concepts for the first phase, because that's a future technology that requires a number of revolutions and new technologies to be invented. But certainly, second gen SBSP, that could be a significant way of decarbonising SBSP.
Cool, lovely. And could you, just whilst we're on the topic of internships and graduate schemes, could you give sort of a short overview of what you'd be looking for in a candidate for these positions?
Yeah, no, sure. It's a really good question, Matt. I think the key thing is, so firstly, you're all at university, you're doing degrees. We're looking for people who can tackle problems, okay, and can think outside the box. We're looking for people who are passionate and really want to learn. My experience, certainly my career, is you never stop learning. And we're looking for people to keep learning through their career with Frazer-Nash and really develop some world-class capability. So passion for learning, being able to demonstrate that, being able to demonstrate you can think outside the box, being able to call on things other than your degree to show I've done this and this is the skills I did. If you can really put that across in terms of any applications, then that will really set you apart.
Cool, thanks for that, James. So the next question is, MROD along with Airbus and ESA demonstrated wireless power transmission at a good conversion rate indoors last month. How far is that technology from being implemented in space?
Yeah, no, so that was a really exciting demonstration. So again, it was, I can't remember the exact, I think it was about 30 meters the distance it was demonstrated over. So we're talking 5 orders of magnitude increase in terms of distance. So it is still some way. So the next step from sort of ground-based trials, you can go on ground, you can go up to maybe a few kilometers, maybe a few tens of kilometers, depending on line of sight. So the next step is to look at that, and then actually what you're looking at is maybe some kind of balloon trial or possibly LEO, although LEO is problematic, because I've mentioned earlier that you've got a very short window before you disappear over the horizon. But then sort of moving to some balloon where you're looking at nearer sort of high tens of kilometers, and then you'd be looking to actually put something into maybe MEO to demonstrate power beaming. But that there's quite a long way to go between from what's been demonstrated both in Europe and in Japan, in particular in terms of some of those demonstrations, and achieving high power beaming over tens of thousands of kilometers.
Cool, great. And I know you mentioned about people in planes and the nature, but we've got a question on a similar trend to that of what impact would it have on nature when you're converting the solar power from space? So I was wondering if there's any more content for that.
It's a really good question. So as I said, the Cassiopeia concept has about a sort of a quarter of the intensity of sunlight, so shouldn't have any material impact. But one of the key pieces of development works that are required is to be able to A, demonstrate that, and B, look at what is a safe intensity of power beaming. What could you actually achieve and still be safe? Because that does have quite an impact in terms of the size of the size of the rectenna and size of the satellite. One of the key things as well, actually, is so the rectenna on the ground is only so efficient, and you're only converting a certain amount of this microwave energy into usable electricity. So you know, what's the impact on the ground there? Are there any benefits? Can you do something else there? Could you co-locate terrestrial PV, for example? So there's lots of things to consider and need further development on.
Cool. And we've also got a few questions around space debris. So we've one from David saying, will space debris be affected with space-based solar power performance and longevity? And if so, how would you mitigate this?
Yeah, no, it's a really good question. And in our cost-benefit analysis that we undertook for ESA and our previous work for BASE on the topic, is we during the 30-year life we assumed a general degradation of the generation you get from a space-based power satellite. Based on you know, loss of PV capacity due to space debris, one of the primary degradation modes. All energy assets, though, you don't build it and then leave it to run for 40 years. Most energy, you know, pretty much all energy assets, you do some form of maintenance on, and sometimes that's preventative maintenance, and sometimes that's forced maintenance due to defects. And actually, the same can apply. The same technology you need to be able to build and put SPSP, construct space-based solar power stations in GEO, is the same technology that you need to be able to maintain it. And I mentioned these things are hypermodular, so you can envision a scenario where actually, you know, you are replacing these modules as they degrade over time. So our initial assumption of a 30-year life, you could potentially extend that out significantly.
Cool. So the next question's from Matteo, and they've asked, what are the attitude and control requirements, brackets pointing error, to reliably target the ground station from GEO?
Now, that's a very good question. This is where, not being a space systems engineer, I can't give the answer. I'm more than happy, though, to take that one away and drop me an email on that one, and I will direct that to one of the guys in the team to answer.
Cool. I was also wondering, I don't know if you mentioned it, but would you be able to rent this service out to pointing at different ground stations, maybe of a different country, if you weren't using it at the moment?
Yeah, so it is an option, and one of the things with one of the advantages of space-based solar power is potentially you could be load following. So as the demand for electricity moves across the globe, so for Europe, for example, so you could, you know, early to mid-evening actually is when you typically see a big spike. In the UK, there used to be a massive spike just after EastEnders finished about 10 years ago. It has degraded, it has reduced as EastEnders become less popular. But you could beam to one rectenna and then beam, you know, move a couple of 100 miles west and follow that load requirement. Whether you choose to do that, because obviously, you know, you're building the ground infrastructure, it means that ground infrastructure is not being used all the time. That is a really good question. There is also the question of potentially, you know, maybe you do something which isn't in GEO and you do something which is in MEO, but you only get a certain amount of power at a certain amount of time, but you have multiple satellites. So there's lots of thinking and development that still needs to be done to really understand what the optimum system solution looks like.
Cool. Great. And have you considered 3D printing for mirrors, PV cells in space instead of assembling?
Again, a really good question. I think the assumptions within our studies is that you build the modules on Earth, and then you take them up, and that's the base assumption that forms within the studies, the cost benefit analysis and the techno-economic assessments we've undertaken. That's not to say that those technologies could not be applied in the future. And as the SBSP development program, you know, hopefully, you know, one of these things actually gets funded and is taken forward, then actually, as other technologies come to the fore, and I know space manufacture, you know, there are some fantastic things going on in the UK about sort of growing semiconductors in space and these kinds of things. Is that about advances? Then that might be one of the technologies which gets folded in So you know, you could print things in space. As I mentioned, you might actually be mining near Earth or near Earth asteroids to actually bring that material to print in space and then print components. So not part of our feasibility studies, but certainly not excluded in terms of potential technologies to be taken forward.
Mm-hmm. And what are the leading companies looking to do this assembly at such large scale?
Yeah, so within the UK, there's so off the back of the Frazer-Nash work and working with the Satellite Applications Catapult, we've formed founding members of what's called the Space Energy Initiative, and the SEI now has about 65 members from UK and Europe, or most with a UK footprint, looking to develop. So get on Google Space Energy Initiative, read all about it. It's really interesting. But some of the key players there, you know, including some of the really large system integrators, are involved in this. So do check out the SEI. You'll be able to find lots more information there about who are the key players.
Cool. And have any end-of-life/decommissioning solutions been proposed beyond keeping the station in orbit indefinitely?
Yeah, so it's an area which is really immature, and I know there are different people, different ideas and thoughts and this kind of thing. What needs to happen is some proper investment and study into this to understand what the potential options are. So yes, so you know, how do you handle things in geo at the moment? You move something into a graveyard yard orbit and leave it there, but actually the value of an SBSP asset itself in just material sat there in orbit, that's of significant value. So chances are you will end up doing something with it. You might not use it as it was intended, you know, once it's been decommissioned, as you're intending to, you know, for power generation. But those constituent materials could be used for other things. You might decide to take them elsewhere. You might actually say take the least degraded components and take them and use them for spares for other systems and space-based solar power satellites. Yeah, so lots of options. Yeah, really, you know, quite exciting, the possibilities that commissioning actually offers.
Cool. Yeah, we are running out of time, so I'm trying to get through the questions as quickly as possible. So they might be a bit quick fire from now on. But we've got a technical one of why is the Lagrange point 1 brackets closer to the sun not being considered as a place for space-based solar power platforms?
Yeah, it's a good question. So the advantage of geostationary orbit is you're always above the same spot, so you can be beaming to the same place where your rectangle is. So not necessarily not the case in other orbits. And also in terms of so I was going to say, yeah, so that's why geostationary is the obvious one. Now, that's not to say that other orbits, other configurations could not be considered going forward, but geo is the primary economic case in terms of being able to provide that constant baseload power.
Okay, and there is a question: what is the results of space-based solar power analysis available somewhere? And Lucy has put a link to a Frazer-Nash UK government shows feasibility of space-based solar power. So I don't know if that answers that question.
Yeah, I will put some. I forgot to put them on my slides, I will admit. No, I will put them in the chat. So, but if you Google space-based solar power and cost-benefit study ESA, you'll find our cost-benefit study on the ESA website. And Lucy's already posted our cost-benefits, our techno-economic assessment for the Department of Business, Energy and Industrial Strategy we completed last year.
And we're getting down to the last few minutes now. So do you intend to use robots to assemble or maintain the station? And if so, how far ahead are these technologies?
Yeah, so principally these the power stations would be assembled autonomously by robotics, and there's lots of ideas about what these could look like, from termites scurrying across the space station to sort of independent vehicles flying around and doing things. So yes, it will be entirely autonomous. In terms of how far we are away from that, we're already seeing in terms of terrestrial applications and drones and ground vehicles and marine vehicles, highly autonomous capability. And there are challenges to taking that capability into space. So, for example, the data fusion challenge, the quality of the data you get. Space is not great for reference points. It's a nightmare in terms of vision, in terms of shadows and these kinds of things. But these are all challenges which in the next 5-10 years we will solve. And it's also aligned with what the industry is trying to do in terms of in-orbit service and manufacture. Those missions, in-orbit service and maintenance, IOSM, these missions will not be driven by humans. They will be autonomous missions, and it's the same technology or very similar technology in terms of autonomous operation that you need to develop space-based solar power. In fact, it's almost easier actually, because you can build space-based solar power stations to be designed by constructed by autonomous vehicles, whereas in-orbit service and maintenance, you're actually trying to do to maintain and refuel satellites which weren't designed to do that in the first place.
That's really, really interesting. And what impact would weather conditions have on the process of sending energy to the ground?
Yeah, so there's two options in terms of how you get the energy from the satellite to the ground. The first one is microwave. The second one is laser. Okay, laser actually, because it requires a far smaller satellite. But the problem with laser is you get significant absorption due to cloud cover. So you don't have that constant power. You are weather dependent. Microwave, effectively, clouds are invisible too. So it makes no difference whatsoever in terms of weather.
Oh, great. And what would be the safety systems against CME or high energetic particles?
Again, that's a really good question, and beyond my knowledge. Please drop me an email. I will send that to our tech team.
Great. So I think that's about all the time we've got at the moment. Thank you very much, everyone, for all your questions, and thank you very much for James for giving us such a great talk and getting through all those questions as well.
Thank you very much.
Thank you so much, James. Really fantastic talk. I'm sure I speak for everyone, and everyone's saying thank you in the chat if you can't see it, James.